Okay, we're going to be doing a brief introduction to confidence intervals based on proportions today. So I'm going to start out by a simple random sample of 30 Grafton High School students. I asked them, okay, are you going to be out the Friday before break? And 11 of them said yes. Now, I've been talking with other teachers. We've been talking about, should we give an assessment or not? And we don't want to do it if too many kids are out. So based on this simple random sample, I can't be entirely confident that this represents my parameter. There's over 900 Grafton High School students. So what I'm going to do is I'm going to create a confidence interval that'll hopefully give me something that'll be close to the true parameter of the percent of kids that are going to be out. Now, before I proceed with the confidence interval, I want to make sure that conditions are met. One of the conditions I want is first of all, I want to make sure it's a random sample. That's important. Is it random? Sure is. You notice it says SRS right up here. Got that covered. So you notice I'm going to put this in quotation marks. Boom, check. Always check your conditions first. Next one, 10% condition. What that means is my sample less than or equal to 10% of my population? Now, as Grafton High School has about 900 students, give or take, I can safely say that 30 is less than 10% of that. Now, the next condition I want met is the large counts condition. So that means I'm going to have 10 successes, 10 failures. So I have 11 kids who plan on being out Friday before break. That is greater than or equal to 10, so I'm good on that large count condition. Now, that means that there are 19 who plan on coming in. That's greater than or equal to 10. So I can now proceed. You always want to check your conditions before you do this. All right, so what I drew down here are all the possible statistics I could have gotten based on doing a sample size of 30. And you'll see right here in the middle, I have my mean or my true parameter here, which is the true proportion of kids who are going to be out on Friday. I couldn't ask all 900 kids. That's why I did a random sample. Now, what I don't know is where does the p hat I got fall? Because the p hat I got was 11 out of 30. Where is that? It could be any of these p hats. I really don't know which one. It could be this one. Could be this one. It could be actually the true parameter. That'd be awesome. It could even be one way out here because, that could happen. We don't know. So the truth is, I really don't know. So what I want to do here is I'm going to create a range of values that will hopefully capture what that actual parameter is. So how am I going to do that? Let's see. I'm going to create a confidence interval. Now, what a confidence interval is it gives you a range of values where you can have a degree of confidence that the true parameter is going to lie. So in this case, I'm going to come up with a range of values that will tell me the actual population of students or proportion of students who are going to be absent the Friday before break. So how do I do that? Well, first of all, I want to decide how confident I'm going to be. I could be 100% confident, but guess what? If I'm 100% confident, I'm going to have a really wide range of values, probably really, really wide. If I want a smaller range of values, it's going to be less wide. The reason is I'm going to be a lot less confident that I actually captured the true parameter. As you can see, there are a lot less p's when I make a range that wide as opposed to when I make it really wide. So part of the balance is you want to figure out what you want your confidence interval to be. I'm going to go with 90%, and what that represents is my confidence level. So I'm going to go with 90% today. You can go with whatever you want, frankly. 90 is a really common one. And what that confidence level tells me is if I perform many random samples of the same size and create confidence intervals out of them, then that percentage of these confidence intervals will capture the true parameter. So if I perform many random samples of the same size, oof, that is awful writing. That's right, it's Friday before break, we're all there. I perform many random samples of the same size, 90% of the confidence intervals based on the statistic I gather will have the true parameter. Now, the key is, now I want to make a confidence interval. In order to do that, I need a formula. In this case, you'll notice when I'm writing true parameter, I should say the true proportion of Grafton High School students who are going to be out before break. So that's what I'm going to change it to. The true proportion of GHS students planning on being out Friday. Okay? So now I need a formula here. The formula for this confidence interval is I'm going to take my statistic, I'm going to add and subtract what I call my critical Z times my standard error, which is going to be p hat times 1 minus p hat all over n. Now I can start filling in blanks. I've got my proportion here, which was 11 out of 30. I can convert that to a decimal, or I can leave it as a fraction. Maybe I'll just leave it as a fraction here. 11 out of 30 plus or minus z times square root of 11 out of 30 times 19 out of 30 all over n. And my n is 30, my sample size. Now, I determined I'm going to use 90% for my critical Z here. So what does that mean? That means is I'm going to build a normal distribution based on my statistic, my p hat. And I'm going to go out and look at the 90% centered around this statistic I have. And that's going to be essentially like a net I'm using, trying to capture the true parameter. I'm hoping the true parameter falls in there. So this represents 90% of my data, right? What I want to think of is what's going to be on my tails here. So that means that's 90% that I shaded in. I'm going to have 10% that's going to be represented by the tails. So I can cut that in half. That gives me 5%. So if I'm looking at the middle 90%, I'm going to have 5% left on each end. So to find this critical Z, again, I'm using a normal distribution. I'm going to go with inverse norm, that nifty function we've used. My area is going to be 0.05. Notice I'm labeling. 0 represents my mean, and 1 represents my standard deviation. Notice I'm using z-scores because I'm looking at the number of standard deviations away. If I plug that in, I'm going to get 1.64. So that's my critical Z. So I can go right up here. I'm going to plug in 1.64. And this allows me to come up with a range of values. And this range of values will ultimately tell me, it'll give me a range where I can hopefully find my true proportion. So I'm going to do one. I'm going to do it out right now. Hopefully you guys are doing it along with me. Again, my confidence level is 90%. I'm going to hit calculate. Boom, and I got a range of values here. And notice it's pretty wide. I get from like 22%, like I'm going to round here a little bit. So I know the true parameter lies between 22% and 51%. So how can I interpret that? What that means is I am 90% confident the true proportion of GHS students planning on being out Friday, being out, I'm just going to put being out, is between 0.22 and 0.51. Might be thinking that's pretty wide. Well, the thing is, I'm looking at 90%. If I have a 90% interval here, I want to make that pretty wide because then I'll be guaranteed, not guaranteed, but I have a pretty good chance of capturing that parameter. In order to catch that parameter, though, I have to be pretty wide. I want a wide net. Now, if I can make my net less wide, I can do that. Like say I want to do that down here, right? I can do that. I can make a, normal distribution based on my statistic. And maybe I want a smaller range. Maybe I want a pretty narrow range here. Maybe I want to go like this. Now, I have a lot less values that could fall in there. So that means I'm going to be less confident that the true P is actually in there. Like, say I wanted to do it based on 68%, like within one standard deviation. That's pretty straightforward. Or maybe I want to be even less confident, but I just want a nice range. So this is where 40% of all my possible statistics could fall. So what am I going to do? I'm going to figure out confidence interval based on 40%. So I'm doing it out. Hopefully you are too. And this time I'm going to go with 40. Now that you want to go with the z-score as well for 40, you got to figure that out. So if you're going to be doing 40%, that means you're going to have 30% of values off of each end here. That would be your tail. So you can do inverse norm based on that. It's always a good idea. Inverse norm based on, let's see, 0.301. In that case, you get a pretty low critical Z. So again, going with the same proportion, my same statistic, but my critical Z is going to be a lot less. And then these values don't change. Still 11 out of 30, 19 out of 30, and it's all going to be over 30. And when I do that out, right, let's go back. A lot of ways you can do this on your calculator. I like going the long way. All right, so now look at this. My range is a lot less. But on the other hand, I'm a lot less confident. So now that my range is between 32% and 41, I can say I'm 40% confident that the true proportion of students who are actually going to miss school on Friday is like 32% to 41. Now, you want to find that balance between, how wide you want your confidence interval and how narrow you want it. I can be 99.7 confident. That is possible. Really, or maybe not 99.7. I'm going to go with 99. But some of my students said that, well, what if we're like really confident? I'll go with really confident here. 0.05. Oh boy. I think I overwhelmed my calculator here. That happens. Quit. Let's get out of here. All right, try again, right? 0.005. Whoops. So if I want to be like 90% confident, right? Oh boy, that's a pretty high z-score. So for 90%, 99, excuse me. I would have 11 out of 30, plus or minus 2.57. Which you'll find that gives you a pretty wide range. The only difference is, the only thing is, it's a wide range, but you also can be more confident in that range. So if I do that out, right? Let's do it. I'm going to get a very wide range here. All right, 99. Yeah, now my range is pretty wide. So, okay, I could have anywhere between 14% and 59% of my students out. So this is, confidence intervals are cool. Don't get me wrong, I love them because it gives you an opportunity to figure out where that actual parameter is. The only danger you have is the more confident you are, the bigger your range is. What I could do, say I wanted to stay 99% confident, but I wanted to narrow down what we call our margin of error. Our margin of error is this. Whatever you're adding or subtracting from that statistic to create your range, this is your margin of error. So if I want to make that, smaller, what I can do is I can increase my sample size. Why is increasing my sample size do that? Well, if you divide by a larger number, then you're going to get less coming out. So say I go out and I decide, okay, I still want it to be less than 10%, or 10% or less, so I go with 90. So I ask 90 kids, and when I do that, I get, let's say, 22 out of 90. So I get that plus or minus. I'm going to keep the same critical Z because I want it to still be 99%. But now I can have 22 out of 90, 48 out of 90 up here, divided by 90. And notice that I can still keep the same critical z, but it's going to make my margin of error smaller. How much smaller? Let's take a look. So let's see, I'm going to do square root of 22 divided by 90 times 48 divided by 90 divided by 90 times 2.57. All right, so now I've got a margin of error of about close to 10%. So now when I do that 22 divided by 90, I get like my 24. I can be 99% confident that the true proportion of kids who are going to be out Friday are going to be about 0.14 to 0.34. So my range gets smaller because I increased my standard deviation. I'm still 99% confident. That was just my phone. So just to recap here, you want to make sure your conditions are met when you're trying to establish a confidence interval. You want to make sure it's based on a simple random sample, less than 10% of your population, and your large counts are met. Establish a confidence level. And what is a confidence level? It tells you if you perform many random samples from the same population of the same size and gather those statistics, 90% of the intervals you'll create, or whatever percent it is, in this case I use 90, whatever the percent is, that percent of confidence intervals will capture the true parameter that you're looking for. Then use this formula. Use your statistic plus or minus critical z, which again, critical z is based on your confidence level, times the square root of p hat times 1 minus p hat over n. And we call this right here, we talked about this whole thing be the margin of error. What we call this is the standard error. So if you ever see the term standard error, that's what they're referring to here. This is standard error, and then the whole thing here, when you multiply it standard error times the critical z, that gives you your margin of error. And then once you calculate your confidence interval, you can interpret it. In this case, I'd said 90% of the true proportion of GHS students, I'm 90% confident it's going to be between these values. But once I got to the bottom here and I increased my confidence interval and I increased my sample size, I could say I'm 99% confident the true proportion of students who are going to be out on Friday is between 14 and 34%. So hopefully this helped you get a leg up on confidence intervals and at least get an idea of what we're going to be working with going ahead. You'll see more videos up as we continue to work, and I'll put up examples as people request them. Hopefully this helps though.